So the last class we had a discussion about this DNL, and we spoke about how this DNL is all related, and yeah, so we did some DNL calculations, and with respect to DNL, we had introduced two different parameters. One is known as monotonicity, and that term or the parameter monotonicity is basically related to a DAC. The other one is the missing code, where it is basically related to an ADC. So we just went on through this monotonicity for a DAC, stating that monotonicity is basically when you try to increment the digital inputs, the output also has to get incremented. Okay, so that is what we said as the monotonicity, and the data converter, or the basically the data digital to analog converter, suppose possess this particular property. Now, if at all, if this data converter or the digital to analog converter fails to have this kind of property, like increment in input digital data, results in a non-incremental shift in the output voltage, then we say that the DAC possesses non-monotonicity, provided if its DNL is less than -1 LSB. Okay, so this is what was being discussed in the previous, probably the last class, and later on we just moved on to the second parameter, which is labeled as missing code, and that is basically related to the term, or basically related to the ADC data converter. So here in this case, I think I was about to explain how this happens, and again, this missing code is a kind of parameter that one could relate to a DNL. So just by looking at a DNL value, one could say that whether the ADC has this missing code or not. Okay, so here is a case where whenever an ADC has a DNL of -1, then it guarantees to have a missing code, and the phenomena could be demonstrated with this picture, with the following transfer function, where you could be able to see that uh, the step size or the step width, basically, okay, for the code that is given as 101, or basically whenever the input falls between this 4 by 8 to 5 by 8, what is happening is that either there is a specific range of input that maps to a value of 100, whereas the other segment, so this particular segment is being remapped to a different data, which is 110. So clearly there is a particular missing code between them, right? So after 101, we suppose to have this 101, and then we have to move on to 110. So none of these input values are being mapped onto this particular code, and that is what we term it as a missing code. And this could be identified by just by looking at the DNL value here. Okay, so in the case, one could evaluate the value of DNL at 5. So which means that we are trying to compute the value of DNL when the digital output is set to have 101. Okay, so in that case, we know that the DNL for an ADC is calculated based on the width. So clearly, you could be able to see that no corresponding data happens here, and generally there is no width at this particular segment. Okay, so there is a 0 width minus the nominal 1 LSB value, and that results in -1 LSB. So whenever we have a DNL which is having -1 LSB, then we have the ADC is said to have a missing code. Okay, so now that we have just looked into all these phenomena, we just move on to the next nonlinear error, which is known as integral nonlinear error, okay. Or in short, this integral nonlinearity can be shortly called as INL. Okay, so in I'll just use this shorter form of INL whenever I refer to this integral nonlinearity. So now theoretically there are a few things, but for the exam point of view, we don't want to consider all those phenomena. So there is something known as a straight line method and end to point method, and we will not touch upon those things just because during your final exam we will not be asking those kind of phenomena like the methods to compute the uh, INL, but rather we will directly get into the way by which an INL could be computed from the DNL, okay, and that is what we will be addressing today. But during the WebEx, in case if you really want to know how exactly it has been calculated during the or basically from the transfer function, we will just look into it. Okay. Yeah. So that's been said. Now let me talk about this INL. So as you could be able to see that the name INL derives from the fact that the integral basically depends on some sort of summation, right. So here in this case, it is the summation of DNL quantities is what the INL basically means. Okay, so I'll just prove that with a very simple statement. Say for example, again INL will have the numbering starting from 1 to 7 for a 3-bit ADC or a DAC, whatever it is. Okay, for a 3-bit ADC or 3-bit DAC, we know that the digital data would range from like would range from 000 to all the way to 111, and whenever the digital data either at the input or at the output, uh, we know that the DNL will always compute it from the value of DNL of 1. So again this DNL of 1 is basically computed for both these cases. Either you are computing the value of DNL for an ADC or you are computing the value of DNL for a DAC, it is always computed with respect to number 1, and it goes all the way up to DNL of 7 for a 3-bit, right. And in the similar way, even this INL will also be numbered from the value of 1 all the way to INL of 7. Okay. So now since because the numbers are varying from 1 to 7, I am just going to define the definition of this INL as an index valued quantity. Okay. That is, I just introduce a suffix I here such that I can write this suffix in terms of DNLs as something like DNL of j, where the j would run from the value of 1 and all the way to the quantity of I. Okay. So as you could able to see, say for example, I just if the index value of I is equal to 1, then the INL of 1 would be exactly equal to DNL of 1. Okay. Now whereas when you have an INL of 2, then the number should start from DNL of 1 plus, right now the current value of I is supposed to be equal to 2, right. So due to which it all the way runs to DNL of 2. Okay. So this is how the INLs are being computed. So in the case where if I have a number like I am just randomly choosing an INL of 4, then it has to sum up all the DNL values right from the value of 1 to all the way till it reaches DNL of 4. Okay. So this is how we compute the INL of a particular index value. Okay. And the value of this I would basically range, as I said, from 1 all the way to 7. Okay. So inclusive of 1 and 7. So now with that, let us try to do a simple problem, one basically on the DAC, the other one is on the ADC. Okay. So let me just try to copy this picture. Yeah, so the picture that I am just pasting here is basically the transfer characteristic of DAC. Okay. So as you could be able to see that the input is a digital input and the output we are expecting is an voltage. So basically it's a DAC. Okay. And now for this we just want to compute the INL. Now in order to compute the value of INLs for these, okay, we have to first compute the value of DNLs, and we have already done this. Yeah, so I think for this we haven't done. Yeah. So now what we will do in this case is to first compute the value of DNL, and for each of the values of 1 to 7, and then later we will just try to use those DNL values to compute the value of INLs. Okay. So, let me just begin with this computation. So, I will write this DNL of a particular index value I can be defined as the actual step, and in this case it is not the width, just because the voltage is applied on the y axis. So, we basically have this V out, an analog voltage that is along the y axis, and due to which we have to compute the heights here. Okay. So, the actual step height minus the ideal step height. Now, the ideal step height is quite easier to remember, which is basically defines the value of 1 LSB. Okay. So, this is always a 1 LSB quantity, and that value for a given resolution DAC can be defined as something like a 1 LSB is defined as 1 divided by 2 to the power n, and since the value of n in this given problem is basically equal to 3, the number of bits, it is defined as 1 by 8. Okay. So, we will just work on with this 1 by basically with respect to this 1 LSB quantity rather than the value of 1 by 8. Okay. Now, in order to compute this the actual height, we have to begin with the number of DNL of 1. Okay. So, which means that we are considering this input value of 001, and then we are trying to evaluate its height from its previous height. Okay. So, we basically try to evaluate this particular height here. So, as you could able to see that the current value when we feed in an input voltage of 001, it is landing up in a space between this 1 by 8 and 2 by 8. Okay. So, which is half the way between these two values. So, which is equal to 3 by 16. Okay. And that is the value that I have between them, and the lower value that I have is basically 0. So, the difference between these two values will give us the step or the actual step height. Okay. So, with that, let me try to write that, and rather than writing in terms of 3 by 16 and stuff, let me write it in terms of LSB. So, obviously, this 3 by 16 is nothing but it is a 1 LSB plus 0.5 LSB from here to here. Okay. So, that is how I can read it. So, from the ground or from the value of 0, I have already 1 LSB quantity plus there is a 0.5 here. So, basically it sums up to a total value of 1.5 LSB minus the previous value, which is this quantity, which is basically at 0, and that is how I write it, minus this ideal value, which is 1 LSB. So, that results in 0.5 LSB. So, the next comes the DNL of 2. So, again I am just going to extract the difference by applying the input as 010, and for that we have an output which is equal to 2 by 8, and basically we have to try to read out the difference between these two components, that is the previous value and the current value, and that gives us a difference of 0.5 LSB. So, I am just writing the value here as 0.5 LSB. Okay. It is the difference that I am writing. I am not or you need to write it as 2 by 8 minus all these quantities, you need to write it. Okay. So, it is something like this: 2 by 8 is the current value and it is not in an LSB, minus this 3 by 16, okay, minus this 1 by 8, and this could be re-returned in terms of LSBs, such that what we have here is a 2 LSB minus 1.5 LSB, and that is, and this quantity gives me the actual height minus 1 LSB, which is the ideal height. So, due to which we have something like 0.5 LSB minus 1 LSB will give us a quantity which is minus 0.5 LSB. So, this is the value of the DNL of 2. Okay. So, I am just repeating this calculation just to ensure that you understand and then do this calculation. Okay. So the next comes DNL of 3, so which could be computed just by looking at the data of 0, 1, 1 and then look for the value that you are getting. So which is again that falls between these two intermediate data, so which would be around 7 by 16 I guess. Okay, so I guess this is 7 by 16. If it is not sure, you can just cross verify this particular value, but I am assuming that this quantity that I have written down is right, and with that I know that this particular data is away from the expected value by 0.5. Okay, so that is how I can write it. Okay, so the expected value for this input of uh, 0, 1, 1 is basically 3 by 8, but what I am getting at the output is basically more than that by 0.5 LSB, okay, by this quantity, and due to which I rate everything in terms of the difference itself. So what I really mean here is that there is certainly a difference from here or from this input to the previous from this output to the previous output, which is basically 2 by 8, and there is a difference of 1.5 LSB, okay, and that is the height that I have, and that height I am just directly writing it as 1.5 LSB minus the ideal height, which is 1 LSB, and that returns us again plus 0.5 LSB. And for DNL of 4, look for the input which is equal to 100, and for this input there is a corresponding output which is landing at 4 by 8. Okay, and what we wanted is just the height. So you just take the height difference from this current value to the previous value, and obviously this will give us 0.5 LSB, and that is the height, actual height, and that actual height I am writing it here as 0.5 LSB minus the ideal height, which is 1 LSB, and that should give us minus 0.5 LSB here. And similarly DNL of 5 is again returned as the height difference. So as you could clearly see that the height difference between these 2 points is basically 0.25. So I just write that it is 0.25 LSB minus this 1 LSB, which is the ideal step height, should give us a value which is minus 0.75 LSB, and we have this DNL of 6. By applying this quantity, we are having, did I, yeah, so this is the 6, yeah. Something is happening here, yeah. So for this corresponding input, we are having a value which is equal to 6 by 8, and again what we wanted is basically the height difference, or basically the difference between this current value of output to the previous value of output. So that would end up having a value which is 1.75 as its height minus the ideal height, which is 1 LSB, and that should give us 0.75 LSB. Okay. And finally we have this DNL of 7, which is written as again the height difference is basically just 1 LSB and minus the ideal step height, which is 1 LSB. So we end up having a 0. Okay, yeah. So these are the DNL values that we have got. Right now our task is to identify the INL. Now the way that one could evaluate the value of INL is, as I said, I will just begin with the value of INL 1, which is basically the quantity of DNL 1 itself will give us, and that is basically equal to 0.5 LSB. The second is INL of 2, and it's basically a summation right from DNL of 1 all the way to DNL of 2. So the summation of these two quantities of uh, 0.5 and minus 0.5 will end up having a value which is 0 LSB, okay, and DNL of 3 could be returned as the DNL of 1 plus DNL of 2 plus DNL of 3, but the other way to write is that I can utilize the previous data of INL, which is INL of 2, and that is actually the representation of the addition of DNL of 1 and DNL of 2. So, I have to add a DNL of 3 to it, okay. So, that is how I can reduce this summing terms, okay. So, we had a INL of 2 to be equal to 0. With that I have to add this 0.5 LSB, and due to which we end up having a value which is 0.5 LSB here, and again DNL sorry INL of 4 can be returned either in terms of completely in terms of DNL or partially the previous value of INL plus the current value of DNL, okay. I will use the second method, like I use the DNL of 3, which is nothing but the addition of all the DNLs till the factor of 3 plus the DNL value of 4, okay. Now, so the previous value of INL 3 is basically 0.5. To this I have to add this minus 0.5, so that would end up having a 0 here, and INL of 5 is INL of 4 plus DNL of 5, and that, and we would end up having a value which is equal to minus 0.75 LSB, and INL of 6 is basically INL of 5 plus DNL of 6, and basically it is minus 0.75 plus 0.75 would end up having a value of 0 at this INL of 6. Next comes INL of 7, and it can be returned DNL of 7, okay. Yeah, so I have to add these two terms, which is basically 0 with 0 will end up having a value of 0, okay. Yeah, so this is how we compute the value of INL in the case of a DAC, and we will just take one more example and discuss about the INL calculation for an ADC. Yeah, so this is basically with respect to an ADC, and so the definition of INL for both the type of data converters remains the same. I just have to add the DNLs, but the way the DNL are being computed for a DAC or an ADC differs, okay. So in this case, since our analog values are staying along the x axis, we have to compute the step width, okay. So the DNL is always defined as, for an ADC, a DNL of a specific value depends on the actual step width here, just because the analog values are falling across the x axis, and due to which we are computing the width minus the ideal step width. So the ideal step width remains the same, so it's supposed to be equal to 1 LSB, and depending on your the resolution of ADC that you use, one could substitute an appropriate value of this 1 LSB by having this computation of 1 upon 2 to the power n, okay. So in this case, this 1 LSB points out to a value of 1 by 8, or a specific value which is I am not sure about this value. Yeah, okay. I hope that you are clear with this 1 LSB quantity, and now let us begin with the computation of DNL. And so let me just start with this DNL of 1, and for this value of 1 you have to look for this digital output, which is 001, and look for the corresponding width, okay. So now in this case the width is computed by this, or the difference between these two values, okay, analog values. So the value that we have here is basically equal to 3 by 16, and the value that I I will get here at the other end is basically 1 by 16, and the difference between these two when you try to compute will end up having a quantity which is 1 by 8, and that is nothing but equal to 1 LSB. Okay, so we'll be utilizing this step width or the actual step width as 3 by 16 minus 1 by 16 minus a 1 LSB value which is 1 by 8. Okay, and the difference actually comes out to a number which is equal to 1 by 8 minus 1 by 8, or you can rewrite this 1 by 8 in terms of LSBs as 1 LSB minus 1 LSB should end up having a result of 0 for a DNL of 1. Similarly, let us try to compute the value of DNL of 2 just by measuring the width, and obviously one could see that there is a width difference of more than 1 LSB, and that value is equal to 1.5 LSB here. Okay, so I'm just going to use the data as 1.5 LSB as the actual step width. Okay, I have not subtracted, but I have just computed this value automatically from the figure. Okay, I am not doing the subtraction over here. It is 1.5 LSB is the quantity that we have, minus the ideal step width is always 1 LSB, and due to which we have a DNL error of 0.5 LSB. Okay. Now next comes the DNL of 3, which is from just by eyeballing you could see that the width of this particular segment is basically just 0.5 LSB, and I just write the number of 0.5 LSB directly over here. Minus 1 LSB should give us minus 0.5 LSB value. Okay. And then next comes DNL of 4. So again, just by eyeballing, I'm just trying to read out the number that is equal to 1 LSB minus the ideal step width, which is again 1 LSB, and the value turns out to be a 0. DNL of 5 would then be again recomputed in the same way, and just by eyeballing I could see that the number would be like 0.5 LSB minus 1 LSB, which results in minus 0.5 LSB. DNL of 6, the width seems to be 1.5 LSB minus 1 LSB, and it turns out to be a number which is plus 0.5 LSB. So finally the DNL of 7 is, yeah, so in this case while computing the DNL of 7 for an ADC, the ideal value is basically 1.5 LSB. Okay, so this is different, and we have to see whether we have a width that is of same value. Okay, so again when you just remap this quantity, you would see that you will have a width value which is equal to 1.5 LSB. Okay, so even the actual width seems to be 1.5 LSB, and the ideal step width is again 1.5 LSB, and all these things happens just because of the offset that we have introduced to ensure that the quantization error of an ADC happens to fall within this plus or minus 0.5 LSB. Okay, yeah. So the end result of this DNL of 7 becomes equal to 0. Now the computation of INL becomes rather simple, and as we did before, I just need to compute all the values of INL, right, starting from the index value of 1 to all the way to 7. Okay. Now I just utilize this. This is basically equal to DNL of 1 itself, and the value of DNL of 1 is basically equal to 0. So even the INL value is also equal to 0, and when the index is being incremented, then one could add DNL of 1 plus NL of 1 with DNL of 2, and which was 0 plus 0.5. Yeah, so basically we end up having 1.5 LSB, and DNL of 3 is returned as INL of 2 plus DNL of 3. So which is 0.5 and minus 0.5 would add up to give a value of 0, and then INL of 4 can be written in terms of INL of 3 plus DNL of 4, which is again a 0, and finally we have INL of 5. Yeah, so this is the computation of this INL. Okay, so hope that it is all clear, and right now we have just done with this computation of uh, DNLs and INLs, and one could actually draw a graph uh, with respect to the value of INLs that we have computed in terms of quantization error. So I'll just try to paste it, and it is not rather difficult to understand. So I'll just paste here. Okay. So as you could able to see that the whenever there is an INL error, the quantization error has some sort of peaking more than the value of 0.5 LSB. Okay. So this is what you would get at the end. And if in case if you have been asked to draw the graph, one has to draw this kind of uh, graph. Okay. Yeah. So the next topic that we are going to discuss is about n-bit accuracy specification. So which is again a term that one could determine whether a particular data converter, whatever they specify as an 8-bit data converter or a 16-bit data converter, is it really a 16-bit or an 8-bit data converter or not, can be quantified uh, by having this accuracy specification. And let me just label this as just as an n-bit accuracy specification. Okay. So this is the parameter that quantifies the resolution of the data converter with respect to the errors. So what it really means is that any error that goes above, say for example, I'm just specifying the error as just epsilon. Okay, so any error that is greater than or so basically it is any error that is greater than this plus or minus half LSB. Okay, and this error could be a DNL or INL or offset. Okay, so any of the error which goes beyond the value of plus or minus half LSB, then one would say that particular data converter has a resolution which is less than by 1 bit. Okay, so what I really mean is that, say for example, I have picked an n-bit data converter. Okay, and if this n-bit data converter has an error with respect to DNL or whatever it is, and if that error is above 0.5 LSB, okay, plus or minus, then the resolution of that data converter is basically not n-bit, but rather it is termed as n minus 1 bit resolution. Okay, so uh, so as a kind of general as a specific example, let us consider that I have a data converter which is a 3-bit DAC, and if this 3-bit DAC has a specific error for DNL, okay, at a particular index value, say for example 3, and if that error value is beyond this 0.5 LSB, then we cannot call this 8-bit DAC as an 8-bit DAC, but rather